So let me give you an example of a bunch of interesting lumped elements, and then show you a couple of really nasty lumped elements. Okay.
I'm going to switch to the other one. I made a mistake.
Okay. So what you see out here, so we characterize lumped elements by their VI characteristics. Okay? You apply a voltage, measure the current. Okay? So what I can do is I can plot I here and V here and see what it looks like. Okay? I can characterize elements by their VI relationship. And there are a bunch of elements that I can create based on the VI relationship. So let me show you a few examples. So for the resistor, since V is directly proportional to I, and R is a constant, I get a straight line. That's the I axis, the V axis, and this is a resistor. What I actually have is a variable resistor, so I'm going to change the resistance value R, and the curve will also change slope. Okay, I change the value R because it's a variable resistor, and it changes slope because my R is different. Okay, next, let me go to a fixed resistor, and this guy here on the screen to your left, I guess, is a fixed resistor. And you see that its IV characteristic is a line of a given slope, 1 by R, and that's it. I can't change it. Number 3, I have another lumped element called a Zener diode that you will see in the 4th week of this class. And the characteristics for the Zener diode look like this. IV. If my voltage goes across the Zener diode goes up slightly, the current shoots up. But if the voltage becomes negative, I don't have any current flowing through it until the voltage passes some threshold, at which point my current begins to build up. Okay? So you can increase the current a little, increase the voltage a little bit, and you can show that the current starts building up again. So that's another interesting lumped element called a Zener diode. Let's switch to a next one called a diode. So diode looks like this, IV. If the voltage across the diode becomes positive, around 0.6 volts or thereabout, current begins to shoot up. But if the voltage is below that threshold of 0.6, then my current is almost 0. It's another lumped element called a diode. And you will begin using these elements in your 002 lives to build interesting systems. Next example is a thermistor. A thermistor is a resistor whose resistance varies with temperature. Okay? So this is a very expensive little dryer, hair dryer. And what I'm going to do is blow some hot air at my resistor, and you're going to see that its value is going to change depending on how much I heat it. So as it cools down, let me cool it down. So you can see it's coming down. I can zap it again. I could do this all day. This is so much fun. Okay, so that's another interesting lumped element. As the temperature rises, its resistance changes.
Photo.
Next thing is a photoresistor. Okay, it's a resistor. It used to be a resistor, Lorenzo. Oh, okay, that's fine. So this is a photoresistor, and notice that it almost behaves like an open circuit. But what I'm going to do is shine some light on it. When I shine light on it, it begins to conduct and becomes a resistor of some value. There you go. Okay? So that's a photoresistor. So now I'm going to show you a battery. Notice we did talk about batteries before. I'll show you a battery. So before I show a battery, just think in your own minds, what should the IV characteristic of a battery look like? IV. A battery supplies a constant voltage. You know, your little cell, your AA battery, 1.5 volts. So think about what the IV characteristic of a battery should look like for 3 seconds before I show it to you. So when I show it, Lorenzo? It's a straight line. This is a good battery. It's a straight vertical line which says that the voltage is 1.5 volts or thereabouts, no matter what current it supplies. As an ideal voltage source. It has a fixed voltage, V, and no matter what the current going through is. Now I'll show you a dud, a bad battery. And this is what the bad battery looks like. So many of you have had your car batteries die on you. And when you go to the store, they check your batteries. They use exactly this principle, that dead batteries have resistance. Whenever you see slopes here, you're thinking of resistance. Okay, they can use this property to figure out that your battery is dead. So that's a dead battery. And finally, let me show you a bulb. We started with a bulb, and so I need to end. Okay. We started with a bulb, so I need to end with a bulb. And what you'll see is that a bulb is simply behave like a resistor. Its IV curve is going to look like this. Okay, notice this is my bulb, and guess what? It behaves like a resistor. It's a very interesting kind of resistor. So I won't go into details for now, but notice its IV characteristic behaves like a resistor. Okay? So those are some pretty standard lumped elements. You'll deal with a lot more set of lumped elements, switches, MOSFETs, capacitors, inductors, a bunch of other fun stuff. But before we do that, what I wanted to tell you is that don't go berserk on this abstraction binge. Okay? Too much of anything is bad for you. So what I'm going to show you is abstractions or models are only valid provided you work within a set of constraints. Notice, we've already had this tacit handshake which said that we'll follow this discipline. Okay? Even after we follow this discipline, there are ranges to how well physical elements can behave like ideal lumped elements. Okay? For example, what I'm going to do is show you a resistor, and it's going to look like a resistor. I'm going to keep increasing the voltage around it. Okay, what's going to happen at some point? I just keep doing that. If it's an ideal element, if you're a theorist, you say, oh yeah, the curve will keep extending till I reach infinity. But this is a practical resistor, so you know. So people out here kind of cover your eyes or something. Okay, so your abstraction can predict that. All it says the current is an amp. It can predict the heat, light, or the smell. Okay, so in the laboratory, when you get the smell, you know what somebody has just done. They've blown the resistor. So that's one example of the lumped abstraction breaking down. So you know, if I really believe in my own BS, anything's a lumped element, so here's a pickle. A pickle's a lumped element. I can treat it as a lumped resistor. But this is a very interesting lumped resistor. Don't try this at home. This is a standard pickle into which we are pumping 110 volts AC. And I promise you, this is a standard pickle. So it has a fixed resistance, but your lumped abstraction cannot predict the nice light and sound effect. So